Is this working? Can you hear? Yeah, it's good. Okay, good. So first of all, this is kind of 3 talks kind of pushed together because I've been down at ODSC today talking to lots of people. So kept it on a slightly higher level. But for me to go into the details, it would be useful to know kind of who I'm speaking to. So is this mainly a machine learning crowd? DevOps crowd? DevOps? Okay. Shout out some ideas. What are you? You're machine learning. Okay. Novice. You're a novice. Okay. Any other answers? I've got machine learning and a novice. Someone that might be doing DevOps. Okay, interesting. So this was the original talk because I kind of wanted to describe what the talk was about. And then as I gave it a couple of times, I got really bored with it. So I thought we'd go with this instead. But then in the conversations I've been having down at ODSC today, I got into a bunch of other conversations around like, oh, is it machine learning or is it data science or is it AI? Kind of who cares? So it's very high level and it's going to apply to some of all of those things. And since I'm bringing up the 90s, it's kind of like story time and then an observation and then like what should we perhaps do next to make things better. So since it's story time, I'll say a little bit about myself first. So now I'm the VP of Marketing for Dotscience, but then I was doing embedded systems in C. And a lot of the story you're going to see today is like the changes that I saw in what it meant to be a programmer or a software engineer and how you would kind of do that work as it went from, let's say, the late 90s until now. And then we're going to have a look at how that might be able to help how we're doing machine learning right now, or AI, or data science, right? Whatever you want to call it. So I guess, who was born in the 70s or before? Who was born in the 80s? Who was born in the 90s? Was anyone born after the 90s? Okay, great. So some of this, some of you won't remember. So when I started in software development would look like this. You'd have like a dev team, and then you'd have a test team. Well, there'd be a design team before that, but don't worry about that. So you've got developers, and then you've got testers, and then you'd have operations. And what would happen is they'd all be like separate groups, and I'd be like typing away, creating whatever I was creating, like a DLL or something. And then I'd give that to a tester, and that tester would go and test it, possibly overnight, but maybe for a week. And then they'd come back with feedback, but I'd already be working on the next thing. And the way that I gave it to him or her was probably by emailing it to them, or possibly by putting it on a shared drive. And it was a bit of a mess. So version control wasn't really a thing then. I mean, some people were doing it, but it was like, you know, you can also just copy stuff around. This creates all sorts of problems. You end up with like the tester coming back and saying, I found a bug. And I'm like, which version? And he's like, mysoftware.dll, and then, no, it's like mysoftware _v2 final v3.dll. And I'd be like, I'm not sure if that's the one I've got. I think someone might have renamed that file in the meantime. So suddenly, it's not very easy to work with them across these 2 silos because what's basically happening is we might be working on different versions of reality. I just did that slide, didn't I? So then operations was a lot of fun as well, because eventually you'd work this out with the testers, and this would take, you know, weeks or possibly months, and then you'd say, right, this is a release candidate, right? This used to be a big thing. You'd have a file that was called a release candidate, and you'd throw it to operations. It might be a DLL, it might be a WAR file, and they'd put it into a Tomcat server somewhere, and they wouldn't have seen any of the development that was happening before that. So they just take it off you. They don't know anything. You don't speak to them very much, like pre-DevOps. And then they deploy it, and it doesn't work very well. And it doesn't work very well in ways that they don't understand. They don't know anything about it. They've got the docs, maybe some logs, but you haven't done any performance testing because it worked finding a laptop, and now it's working at scale, and this is a huge problem. And this is like after the testing cycle, now it's in operation. So it could be 2, 3, 4, 5, 6 months between you writing it and them deploying it. And now it's not working correctly, and you can't even remember anything about this. So when it doesn't work, you can't communicate with the operations people to get it working again. Everybody is sad. So we could go into more details, but I think you get the idea. Like, things were not very good. But of course, we still ship loads of software, right? There was loads of software that came out in the 90s that people bought for huge sums of money. And how did we do that? Well, we did it very slowly, right? We had release cycles that took months. A yearly sort of release was not unusual. And we had things like CCBs, change control boards, where you'd go and make a change, and before you're going to do a big new feature, you'd go to speak to the change control board. It was like a central sort of architect type team, and they'd look at what you were planning, and they'd figure out how that might fit into the whole software. And everything was slow and incredibly painful, right? Most software companies were forced to choose between speed and safety, and they had to choose safety. You had to do things extremely slowly. So we mentioned reproducibility in the first title. What has this got to do with reproducibility? The whole point about making software in general is that it's mainly debugging, right? You write something, then you figure out what went wrong, and then you do that a lot. And that's in local development, then also in CI, but then also in production. We're constantly pushing out new ideas, iteratively figuring out whether or not it was the right idea. And how do we do that? What we do is we try to reproduce as many of the variables as possible and see what changed and see why it doesn't match our expectations. So being able to reproduce a known state of the world is core to how any software engineering is done. So obviously now we have things like Netflix, right? Apparently they're deploying 1 million times per millisecond or whatever we read in the news. And they're also up most of the time. So somehow they've improved a lot of things. So how have we done that? How have we gone from this situation where I work locally, wait months, and then have bad results? So I put this one in because some of you who weren't working software at the time might not believe me that it was this bad. This used to be called the Joel test. Anyone working like the early 2000s, mid 2000s in software? Yeah? Right. So this was seen as an aspirational goal for a lot of teams until even like 2005. Do you use source control? Right? That was an aspiration. Many teams, this was like, shit, you got all 12? Unbelievable. Now this is laughable, right? And it's really not that long ago, like 13 years ago. I was at a company that definitely didn't get like 6 of those in 2005. So we've come a long way in a relatively short amount of time. So I want to make a quick note about collaboration, because the point about like, why was it going wrong with me and the testers, and why was it going wrong with me and the operations people? Well, it's like, why do I need to speak to them in the first place? It's because we need to collaborate with other people. And there's 2 kind of ways you can do collaboration. It's constructive or deconstructive. Now, deconstructive is very simple. I send you a copy, and now we've got 2 realities. So when we have to debug something, we have to figure out which one. Right? Constructive collaboration is very simple. It's called version control. And it's kind of taken for granted, but it's actually quite magical. So everybody uses version control now, right? Well, I guess the machine learning people in the room might not, or I would argue they might not. But does anybody not use version control? Does anyone not start a project by like Git init or similar? Right? Everybody does that now. So we've gone from it being an aspirational goal to just a matter of course in like 13 years. You say sane people use version control. I mean, I think a lot of people don't even know why they're doing it. You just do it. It's a reflex. But it enables a lot of things. So like, without version control, you can't have continuous integration, right? Because what would you be continuously integrating? You can't just throw random code at a CI server and see what happens, because when something breaks, you need to link it back to a commit. Where does a commit come from? Version control. So it's enabling that first step in a continuous delivery pipeline. How does continuous delivery work, right? You throw code into GitHub or wherever. It gets pulled out and built, tested, and then built into an artifact. That artifact's now going to be delivered into acceptance or staging or production or whatever you want to call it. If something goes wrong, you find out which Docker image comes from which commit. It goes all the way back to reproducing the state of the world. Which thing is broken, and how can we get it back to an actual change that happened in version control? So earlier I said, you know, like everything was absolutely terrible in the late 90s, but we still got software out. How did we do it? We did it by going very slowly. Now by having things like CI, CD, what we can do is we can go fast and be safe. Because what we're saying is, we're not saying, like, let's put loads of upfront preparation in so that nothing can ever break. What we're saying is, Let's just throw loads of shit at it, because if it breaks, we can fix it really quickly, right? It's a kind of different way of thinking about safety. And by thinking about it differently and being able to track everything back to a reproducible state of the world, it means that we can do that. So the question is, if software development was so bad in the late 90s and now it's so good, how is AI/ML/data science doing? Now, at ODSC this morning, this got a huge laugh because they all were feeling incredibly guilty. But it didn't work out here, so I'm going to have to find a laugh somewhere else. So we've been speaking to loads of data science teams, people beginning with machine learning, people doing data science and calling it AI. And here are some of the anonymized quotes. Some of the things that are starting to happen now is like people will work on, I don't know, they'll come up with this idea like, we've got a load of data, we can probably do something smart with this. And I've heard about PyTorch, so let's go and do some stuff. And then they do that, but they do it in the same way that I was programming in the late 90s, right? You hack it away on your laptop and you think that kind of works, and then you throw it somewhere. But in some industries, you're going to get audited, right? So they've kind of been doing like R&D for a while, but now the auditors are looking at them and they're saying, well, that's great that you've come up with this thing on your laptop that's never been tested and you don't know how to redeploy, but how do I know what it's doing? And how can I trace it back to an actual change that you made so I can find out what went wrong if something goes wrong? This is very common. If you can't reproduce a working state and you have some people working on data science problem, then they leave the company. There's no way to get back to what they were doing, right? Half of it's in their heads or all over shared drives or possibly on the hard disk that they walked out the door with. In terms of observability, I mean, this is very, like everyone would know the name of this company. They put a model into production and went, that's done now, that'll be fine. But it was touching billing. Now, I mean, obviously it's not measurable because they're still in business, but I think they were trying to impress upon me that it was a lot of money. This is the kind of level we're talking about, right? After the last audit, I was surprised by how many problems in the audit we could have solved by keeping paper logs. But if we ask the data scientists to do that, they will leave. This is a relatively large company with lots of money, and this is what's happening. This is one way to do collaboration, right? Keep them in a small room so they can talk to each other. Now, that probably works very well and may even work better than like bringing in loads of processes and tooling. But if you want to have more than 3 to 4 people working on a problem, it's not going to work anymore. So we had this idea of like destructive versus constructive collaboration before, and I've shown a few examples there. Destructive collaboration is very normal. We see people like emailing each other IPYMB files. See people like sending massive CSV files through Slack attachments. Like it's what's that? That's an American saying, right? Shit show. It's a shit show. Automated testing is very rare, right? Because it's still seen as the domain of an individual data scientist a lot of times. So you get it working locally and then you're done. Right? So we don't apply like any of the tests that we've kind of built up before from things that we've seen going wrong. So we just say that's fine and we push it out. Deployment looks a lot like it used to. You end up with a model, which is various formats. You give it to someone and they put it in a place where it runs. Continuous delivery is rare, although actually for all of these, I mean, the problem is the space is moving very quickly and there are clearly some leaders. When we speak to people like Lyft, Airbnb, Uber, they've fixed all this by putting big teams on building internal tooling. And that's fine, and that is possible if you've got that kind of money and that kind of engineering inclination and talent. But most people in the industry are not going to do that, right? They're going to have this buy versus build, or like build versus use someone else's open source decision to make. But before they even make that decision, they need to be aware of the problem that's coming their way. So again, to kind of hit on the point, how are we delivering any of this stuff if we're not Uber and Lyft and Airbnb when everything's such a mess? Well, we're doing it very slowly, right? There's an awful lot of like, write the docs. Have you tested it 20 times locally? Like, who do I call if anything happens? What should I look for? Like, it's this very manual process that resembles the sort of caution you saw in software in the late 90s, early 2000s, because we didn't have the processes and tooling in place to give us the reassurance that we could just throw code into version control and then deliver it out and everything would be fine. And we don't want things to go slow, because the reason why everyone's here, you know, we had this talk earlier about machine learning. Everyone down at ODSC is doing machine learning something. The reason why is because people are understanding that this is going to differentiate companies in the not too distant future. And if you're not very good at it, you can have all the data you want, but it's not really going to help you in the marketplace. So the question then is, how do we get AI and ML and et cetera, yeah, I was getting tired, out of the 90s? So as I said earlier, like version control, even though it's something that we take for granted, is actually fundamental to most of the practices that have brought software engineering from the late 90s to where we are now, because it enables us to get back to that single atomic reproducible state so we can figure out what went wrong. It enables that fast iterative cycle. So yeah, that's kind of what software has been, right? It's like, how do I get from dev to production as fast as possible and test ideas against the market? If you're releasing once every year, your market research better be good, because if it's not, like next Christmas you get to have another go. Right? This sucks. So why don't we, this is really annoying, let me go down there. So the problem is, if we want to bring version control in things like AI, ML, data science, et cetera, it's kind of different to just doing it in code. If you're using Git, normally you put your code in there, maybe some tests, maybe some small test data, but it doesn't work in machine learning because like files are too big, we need to track other things like parameters. There's a lot of other things going on. We'll come back to that in a bit. The kind of things that we expect to be able to do on code are different when we're doing machine learning, because you can't just diff a model, or you can't even diff a Python notebook, right? How are you going to do that? Like pull out the bits and then diff them? Like, we don't have tooling for this. It's not a difficult problem, but it just doesn't exist. Continuous integration is very different. So, you know, we can talk about different types of testing, the test pyramids and things like this all day long, but basically, you know, you're going to throw code into Git. It's going to be pulled out by Jenkins, GitLab, whatever you want. It's going to do unit tests, right? Maybe some component tests. End-to-end tests normally come a little bit later, but they're all very deterministic. You get a yes or a no. How are you going to do that with a model? Well, I can put the training data in and see if it gives me the same thing, but that's not really testing. I just did that. So I have to give it something else. So it starts to look, CI in this world starts to look a lot like monitoring and production in the normal world, where we have to look for outliers. We have to put stuff through and say, is this normal? Is it more than n standard deviations away from what we expect? Because the whole power of these things come from the fact that we don't know exactly what they're doing, right? There's a lot of inputs we can put in that we haven't predicted. That's the point. They're going to predict them for us. So this becomes very difficult, and we don't really, no one's really looking at this, as far as I can tell, apart from those companies that I mentioned earlier that have clearly gone ahead and built it. Continuous delivery actually doesn't look that different in this world than it would in a normal code world, because when you get to production, you're sort of touching reality, right? So it becomes non-deterministic again. You don't know what's going to happen. You end up monitoring and looking for outliers. And this is this thing I was talking about earlier with like mean time to recovery instead of mean time between failures. The old idea used to be, let's never fail, so we'll be really prepared so nothing ever breaks. The idea now is, don't worry about that. Make sure that you can fix it in like a minute, and then if it does break, nobody cares, right? And it seems like, you know, just changing that mindset allows a lot of the progress that we've seen. Observability, I mean, I don't really agree with this slide anymore, so go to that. So, like, if we're going to fix this, what's the big vision? So, if you agree with me that version control is the basis for a lot of these practices that have enabled us to take software engineering from, like, I don't know what was on TV at the time, Friends, to House of Cards, let's say, then that's a bad example, isn't it? Let's not go with that one. Damn, Taxi, yeah. We're going to start in development because that's where all this kind of thing starts, right? If we're not version controlling the code or the machine learning or the data science or the AI where it's being done, then it's not going to go down the pipeline. So we start there. Now, if we want to, white slides again. What do you need to version control if you want to get reproducible data science, AI, ML? What is that? Oh, no, it's fine. It goes back to black soon. So, like, there's a few things you got to do. So, if you actually want to be reproducible, you're going to need the environment. So let's say like at least the version of the kernel you were running on, some of the libraries on top. You're going to need the code, whether it's notebooks or whether it's just code, plus parameters to models. And you're probably going to need like version training data that you use to get to that point in the first place. That's better. So how do we do? Well, like I met Victor through Docker, right? This is now, I'm sure like some people still think that Docker's new, but I'm sure that's not happening here. Docker's great for this, for an environment, right? You give it a kind of kernel and then all the dependencies, and that'll always be the same, unless it's breaking IPA change, but that's different. For like notebooks and parameters, we can just use Git, because it's text, and that's what Git's for, right? The problem with Git and data science is like a couple of things. One of them is typically when you're building these models, especially if you're working in a notebook, you don't really think in that same way, like change a file, add it, commit it, push. Like you kind of want something to be just tracking what you're doing, almost like an autosave kind of thing every now and again. And then every now and again, you'll collapse all those and you'll say, right, that was a good idea. I'm going to go with that. Let's make that a commit and push it. The other thing is, and this is something that we see a lot, is like you'll have data scientists have come from all sorts of strange places, right? They've come from like business intelligence in the marketing team, and now they're doing data science in a central place in the company. And people see that it's going wrong, so they bring software developers as DevOps people in to help out. And when that happens, they say you've got to use Git. And then they try and put a file that's larger than 100 megabytes in Git, and then everything is painful. But have you done this? You just winced when I said that. Okay, fine. So Git doesn't like large files. It's not built for that. Now, you can use something called Git for large files, and what it does is just like store the hashes of S3 buckets. But that's not great, because if I'm working on a terabyte of data and I make a 1 byte change, I'm not going to push terabyte bucket back up to AWS, and you've got to pull it down, and everything's going to be slow and terrible. So, yeah, and I suppose that's a good point, right? Like, it's not just about versioning. Like, if we're going to have a Git-like workflow, we're going to need to be able to branch and diff and merge. And these things just don't apply very well to sort of large data sets or to Jupyter Notebook or to RStudio files, whatever they're called. So our proposal is this. Now, we released this open source tool called .mesh. And what .mesh does is it basically presents an interface that you would expect from Git, but it scales to arbitrarily large file sizes. Now, arbitrarily large means we've tested it to 10 terabytes. If you're doing more than that in development, you probably need to be working on smaller files at the same time. So what it does is it's kind of like Git, and you could use it that way, but because we're using it specifically in this area, we can sort of infer some things about what you might be doing. So when you're adding new input data or code or other things in there, we can tell what they are. And then we can build cool things like that on the right. It's like a provenance graph. So we can say these files went into those processes, which became other files, which became the final file, which is kind of useful if you later want to go back and recreate what happened to get to a model. Because it's not very often that you have like training data model, and then that's it, right? Very commonly, you're deploying many of them together, seeing which do the best. So these sort of, I mean, does that count as a directed acyclic graph? I think it does. It's a DAG. DAGs are useful. So that's it. That's kind of it. But it's such a nascent field, and there's lots of people doing things in different ways. And the number of people we've spoken to, like a tiny percentage of who we need to speak to. So my real wish for this evening is that I'd come and like say loads of words, and then people would come and say like, hey, I'm doing that, and that sucks, or I hate your idea, Mark, I'm solving it another way or something. So I'm really here to just learn, because it's moving so fast, and people are doing it in so many different ways that it's really hard for us to pick sort of product direction. Now, just to point out the difference between Dotscience and .mesh. .mesh is the open source primitive that you can use for version control to arbitrarily large files. Dotscience is the product that you can use to do that, but then sort of on-prem, on your cloud. It integrates to a lot of other things, and it's the kind of thing that businesses need when they don't want to build it all themselves. That's it. Thank you very much.
Cool. There's a question on there. it is working.
Thanks a lot, talk. I think every slide I was just I I work with software, but I pretty much similar tooling for Spark. So CI get Jupyter, their work totally bunch of stuff
Right.
to get out of.
And you work where? Microsoft.
I work.
That's great news. We should talk.
Yeah, and I think we have built this. How much success you have seen? What do you do with pushback?
How much? Sorry, could you repeat that question, please?
So I have
yeah.
Sorry. With data science, what I have personally seen, like all the new tooling, for example, Docker and Kubernetes, brings a lot more sort of totally different dimension that they never have.
Yeah.
And the AI data itself is moving fast, and they are learning a lot. That I just like. Do you have any experience on like how to sort of help them?
How they're approaching that? Yeah, it's difficult because what we see is that in a lot of places, data scientists sort of left in the cold a bit. So a lot of development teams will have DevOps teams, and we can talk another time about why a DevOps team is the stupidest idea ever. But
by the way, I use a term called AI ops.
AI ops,
that
right?
Seems like one way that's different than DevOps divide was sort of broken by DevOps AI, and like the product silo is broken by.
Yeah. So this morning at ODSC, the term ML ops came up, but it seems to be covering the same sort of thing, which is like, let's take all the things we've done through those years and then apply them to this space. And I think the specific advice for teams that are there and want to get somewhere else is that you always have this problem. Like, let's imagine you have some sort of iterative development process, kind of agile vibe, right? So like doing things in weekly sprints. The problem is you're always going to have like how much feature work should we do and how much like technical debt should we do? And this is like 20 years of technical debt, right? So you're gonna have to get that in slowly. And the way that I've seen people do that successfully is within the definition of done for a thing each week. They'll say like this week it just has to work on your laptop. Like a month from now, definition of done includes it's on CI. And then like 2 months from now, the definition of done includes being deployed all the way through to a staging environment. And then like 6 months from now, it has to be deployed all the way through to production. And what that means is like you just constantly move the goalposts in a way that doesn't mean like we've all got to do CI. It's like, no, next week you're going to have to get it to CI so people can prepare themselves for it. And I think on the process management level, that's smart. And then obviously you've got to get like people in there that can help because a lot of people in this space are specialists, domain specialists, and they don't want to, nor should you ask them to set up Kubernetes. Yeah. Thank you.
Yeah, I was just wondering if you were going to be presenting these ideas at either the AI Frontiers conference or Scale by the Bay, which is about a week.
I was really hoping to go home on Friday, but I guess I could. But what was the first one?
AI Frontiers
starts
in a week.
Right.
In San Jose, and Scale by the Bay will be up on
Market Street. Yeah, so it seems that there's just loads and loads of these conferences. I have to be in Shanghai next week for KubeCon, so I won't be able to do that. Yeah. For the CNCF.
I'll be at Scale by the Bay, by the way.
Oh, there you go. Go and say hello.
I had a question too. So you talked a little bit about continuous integration, but what about continuous training? Like if what you're doing is you keep on training your model every single time there's a little piece of new data, how do you make sure that that doesn't break some?
Yeah, so I was thinking about this, and it's like if we have this thing here, right, so let's imagine that you're continuously training models, right? So if maybe you have new training data, or maybe someone wants to change it slightly, right? So there's got a constant flow coming through here. But at the same time, you've also got like, if we agree that the only way to test this correctly is by looking for outliers, then the thing testing it's also sort of a model, right? So actually you've got like code going through there, and then another pipeline that's going through here to bring in new tests that know about And how that works, I don't know. I don't know how that works, but that's probably what's going to happen.
Yeah, because like what I wonder is if you're doing continuous integration of code, you can always fall back. Like you can revert the change and go back to what you had before.
Yeah.
But reverting data seems like, is that something that you support on .mesh? Like saying, hey, this change on the file that we've done before, actually forget about it.
Yeah, so this thing here is kind of visualizing here, there. So what you're seeing, the gray things are processes. The other things are data. I'm totally colorblind, so I'm not going to try and guess what they are. That @ on there is a hash, that's version. So what you could do is you could freeze everything apart from that. But I mean, it might not work because it might be a different schema. So, you know, it might not make any sense. But theoretically, you can take any of those variables. Like, you can imagine it's the z-axis going back through the screen in that time, like negative time. And yeah, I mean, theoretically, you could go and do that. Typically, well, I've never seen anyone do that, but that might be the way to do that. But that's actually a really interesting point. I don't really have a very good answer.
I have a second question, which is actually very, very related, which is in .mesh, you say that you handle data efficiently, like large data efficiently. Does that mean that if I change single byte in a 1 terabyte, you're going to store only 1 byte? Are you going to be pushing 1 byte or 1 terabyte?
Yeah, I mean, it's not like, I can't promise you it's going to be 1 byte.
But like no 1 terabyte either.
It's
like
going to be significantly less than a terabyte.
Okay.
Yeah. I mean, it's almost exactly analogous to the Docker copy on write thing, but we don't really have layers, so we don't care about that. We just have blocks, basically. So we can do a much better job of diffing. Yeah.
Thank you.
Actually, last month I gave a talk with the title "The Quest for Data Science Principles," and it's going in like the same direction.
Right.
And one thing which we also saw when implementing that with like large enterprises, it actually makes the data science more productive, because once they actually do the git commit, which unfortunately is like git right now, but they don't have to worry about setting up system training, hyperparameter optimization. This is all captured by the CI.
Right.
They can actually focus on writing really cool models. So it actually made a significant impact on activity.
So they can send the commit and know that that's atomic, and then have all sorts of automated things happen without.
So basically, the artifact we used there is like MLflow project.
Right.
And when they do like their commit on their MLflow project, this triggering CI is automatically building hyperparameter optimization, all this kind of stuff. And we're not at CD yet, so we're not deploying automatically.
Yeah.
But that's working rather well.
Yeah, that's a really interesting point. So I suppose there's a lot more you could do in the CI stage than I mentioned here. I'll go and read your talk.
I already sent you my slides.
I know, you sent it a week ago. I'm sorry. Is that it? All right, thank you very much.